Welcome to Lecture 3.7, Tensors. The formal definition of the tensor product of two vector spaces is quite abstract. However, the concept that it represents is actually fairly straightforward, and this is really well illustrated with some choice examples. So throughout this lecture, we will consider two vector spaces, U and V, over a field K. Let's say that U is n-dimensional and V is m-dimensional. It will be frequently helpful to think about these as vector spaces of polynomials. So let's say that U is isomorphic to the space of polynomials of degree less than n in X, and V is isomorphic to the space of polynomials in the variable Y of degree less than m. So I will use AIs for my coefficients in U and BIs for my coefficients in V. Since the tensor product is a product of two vector spaces, it's worth revisiting our familiar direct product U cross V. Now, using these same U's and V's, a basis for this consists of all ordered pairs with x to the I in the first coordinate and a 0 in the second coordinate, along with the ordered pairs that have a 0 in the first coordinate and a y to the j in the second coordinate. So clearly, the dimension of the direct product is additive. In other words, the dimension is the dimension of U plus the dimension of V. The tensor product is going to have a multiplicative dimension. So in other words, the dimension, as we will see, of the tensor product of U and V is going to be the dimension of U times the dimension of V. So we will think about a basis of this, and we will construct it by taking products of basis elements in U and basis elements in V. So more on this shortly. Returning to the direct product, an arbitrary element is just an ordered pair of a polynomial in X with a polynomial in Y. Notice that, in particular, the ordered pair 3xi, yj is not equal to xi, 3yj. In other words, the 3 does not go back and forth. And to see this more concretely, it is certainly not the case in R2 that 3, 1 and 1, 3 are equal. So these are not equal, clearly, as vectors in R2. And that's just a general property of direct products. In addition to the direct product, there is another way to multiply the vector spaces U and V together. It's easy to check that the following is a vector space. So the set of all sums over x to the I times y to the j. So in other words, in here, we might have an element of the form x squared minus y cubed plus 14x to the fifth y plus 16xy squared minus 14. So something like that is going to be in here. This is the idea of the tensor product, which is denoted U with this little symbol V. So we'll say U tensor V. Now, formalizing this is actually a bit delicate. For example, compare to up here where the 3 does not cross over to the other side. 3x to the I times y to the j certainly equals x to the I times 3y to the j, which is just 3 times x to the I times y to the j. So this is really just the associativity property, but if we think about the tensor product as like ordered pairs of things in I times things in j, then it is the case that 3xi, yj is going to be, I'll put equals in quotes, equal to x to the I comma, or actually the I times 3y to the j. So because of that, we are not going to use this ordered pair notation. We're going to use something else. So this example of polynomial vector spaces I like because it really is, in my opinion, the best way to visualize what the tensor product is. Normally in a vector space, we are not allowed to multiply vectors together. And especially if we have two different vector spaces, we can't multiply vectors in here times vectors in here. Especially if we're dealing with R3 or R4, that doesn't necessarily make sense. But if we're dealing with polynomial vector spaces, then it actually makes a lot of sense to multiply things together. If we multiply two polynomials, we get something like this. And that's clearly a vector space. And that's really what the tensor product is all about. But the tensor product will generalize this to arbitrary vector spaces. So even though it's weird to think about multiplying vectors from, I don't know, R8 to R9 or something like that, we can do it using this formalization, and it's really the same thing as if we had considered these things instead of like E1 up to E9, we had considered these things to be polynomials, 1x all the way up to x to the 8. So throughout this lecture, I want you to, when it seems abstract, when there's certain relations or certain ideas, I want you to think back to these polynomial vector spaces and as motivation for why the things that I'm presenting should be true. Since we are not normally allowed to multiply vectors together, we define a special symbol to do it. Now for polynomials, we don't need that, but for all other vector spaces, it makes sense. We will denote the formal product of two vectors, u and v, as u tensor v. So we use the same symbol as we do for the entire space, big U tensor big V, but here we're using vectors instead of vector spaces. Let's pick bases for U and V. Let's say U1 up to UN and V1 up to VM. One way to define the tensor product of U and V is as the vector space with basis UI tensor Vj. So this is a nice and easy definition, and it really is a generalization of the idea of the space of polynomials of the form Cij times x to the I, y to the j. I mean, it's the closest thing we have to just abstracting this definition right here. However, it does have some disadvantages. First of all, the definition depends on a choice of basis. And in theory, it would be nice to have a way to talk about the tensor product of two vector spaces that was basis free. And we'll do that shortly, but for now, let's say a couple more things about this definition. So by construction, every element can be written uniquely as a linear combination of UI tensor Vj. So there's going to be n times m terms like this. It is immediate that dimension is multiplicative. In other words, the dimension of U tensor V is the dimension of U times the dimension of V. Let's pause to make a few observations. First of all, not every multivariate polynomial in x and y factors as a product p of x times q of y. So going back to our more concrete examples of a vector space of polynomials in x and y, let's take 3x squared minus 2x plus 4 times y minus 1. So this factors as 3x squared y minus 3x squared minus 2x y plus 2x plus 4y minus 4. Now, the analog of these tensors of basis elements, ui tensor vj, are the monomials without the coefficients. So I'm going to box them over here. And it is true that every element, well, here we have a 4 times 1, every element here is going to be, in the tensor product, is going to be a linear combination of these things. However, this one is special because it factors as an element here which is in U and an element here which is in V. Not all elements will have that form, and that's what we're saying right here. For example, if we take the x plus y, this is a polynomial in x and y, but it cannot be written as something in x, p of x times something in y. It just can't be factored. Now, it can be written as a linear combination of, so it can be written as, let's say, p1x q1y plus p2x q2y. For example, if we say x times 1 plus 1 times y, that works. So elements that can be written as a single product, say abstractly u tensor v, or in this world something in x times something in y, are called pure tensors. So the tensor product u tensor v is going to be consist of the set of all linear combinations of pure tensors. So this is one is not. Now we will introduce an alternate construction of the tensor product, and this one is basis free. So given vector spaces u and v as before, we will define the so-called free vector space over the set u cross v to be the vector space whose basis is the Cartesian product u cross b. Now this is a little bit weird to think about because that means that, say, x0 is an element, y0, no, sorry, not y0, let's say 2x0 is another element. If we add those together, we do not get 3x0 because these are linearly independent vectors by construction. So this notation does not suggest that. This notation suggests that you can add them up. So we are going to use a different notation. We're going to write this as like x0 plus e2x0, which is not equal to e3x0. So this is a linearly independent set. Now we'll actually drop the parentheses and write it just as e comma or eu comma v. So elements in the free vector space are finite sums or finite linear combinations of the basis vectors. So c uv e uv, where u is in u and v is in v. Now we are trying to construct the tensor product. So right now we have this huge vector space of all of these basis vectors and no relations. And we want relations. We want our standard relation to hold. So we want x0 plus e2x0 to equal e3x0. This is something that we want to hold. We also want our bilinear relations to hold. So we want, so look at this and think that what we want this to be, this is going to represent u plus u prime tensor v. And this here is going to represent u tensor v plus u prime tensor v. So right here there are no relations, but we will add relations, and we'll do that by quotienting by a certain subspace, and the equivalence classes are going to end up being the elements of the tensor product. So we want to force an element like this in the quotient to be equal to the sum of these two elements. In other words, we want bilinearity, or I guess we want linearity in the first coordinate and linearity in the second coordinate. Again, you can think of this as u tensor v plus v prime equaling u tensor v plus u tensor v prime. And this one here as cu tensor v, we want that to be c times u tensor v. And we also want that to be equal to u tensor cv. So we want these things to hold. So what we will do now is take the set of all so-called null sums in here. So notice what this is here. So this is obtained from this first equality over here if I move everything on the right-hand side to the left-hand side. So we want to force this equality, we need to force this element to be 0 for all u prime, and v. And similarly, we want the same thing for these other relations as well. So S is going to be this giant basket of all of these elements which we need to be 0 in the quotient, that is in the tensor product. Now we will let NQ be the subspace of the free vector space spanned by S. And we are going to quotient out by this, thereby forcing these relations, or all of these elements, to be 0, hence forcing these relations. Think of this as when we construct z mod 12z. So we take the integers and we mod out by 12, and we get something that this is a group, but you still get the same idea, z mod, z12. So this is like the integers mod 12, like when we're telling time. So we are literally taking the subgroup of all multiples of 12, and we are forcing 12 to be equal to 0. That's what happens when we quotient by it. So the name NQ here suggests that it is, Q stands for quotient map. So literally Q is the map from the free vector space to the free vector space quotient NQ. That just sends an element, the direct sum C U V E U V, to itself mod NQ. Of course, this is an equivalence class, and we will denote the equivalence class of EUV as U tensor V. Now we can define the tensor product of U and V to be the quotient space of this free vector space mod NQ. Let's now verify that our basis-free construction of U tensor V actually works. Even though we didn't use a basis in the construction, we can still, after the fact, speak of a basis, say U1 up to UN and V1 up to Vm. And what we want to show is that UI tensor Vj is a basis. In other words, that this has dimension n times m. Now remember, our free vector space F U cross V has elements of the form CUV times EU comma V. And then in the quotient, when we mod out by the giant set of null sums, what we get is equivalence classes. And we call those equivalence classes tensors. So U tensor V, that's the symbols that we used. And so these are the elements that so even though our construction was very different, our elements are still the same. They are finite linear combinations of pure tensors. Okay, so what we will do is we will construct an abstract vector space with basis Wij, where I goes from 1 to n and j goes from 1 to m. And then our goal is to somehow come up with a bijection between the Wij's and UI tensor Vj. Now we can define a linear map alpha from W to U tensor V that sends Wij to UI tensor Vj. And since we defined this on the basis vectors, we can extend it to be a linear map on the entire space. There's no problem with this definition. So all we have to do is show that this is a bijection. That is one-to-one and onto. Now that's hard because we don't really know exactly what a basis for this looks like, and it's hard to deal with. So another method of showing that something is bijective is to show that there is an inverse map. And so what does that mean if, let me call this inverse map beta, this our attempted inverse map. And what that means is if we start at W and we first do alpha and then beta, that's the identity. But we also need that if we start over here at U tensor V and we do beta and then alpha, we get the identity as well. So in other words, what we need is if we do alpha of beta, that is the identity on U tensor V, and beta of alpha is the identity map on W. So I encourage you to verify it for yourself that this is equivalent to alpha being bijective. So how can we define such an inverse map from U tensor V to W? To do that, we would need a basis for U tensor V. Now, what it's going to end up being is literally sending UI tensor Vj back, but we don't know that this is a linearly independent set from our abstract definition. And we cannot just arbitrarily define a map on a set of vectors and extend linearly if we don't know that set of vectors is linearly independent. So for example, if I have a map from, say, R2 to R2, let's call it A, and I send, say, E1 to, I don't know, to 1, 1, so this is AE1, then then 2E1 is forced. It has to get sent up here. In other words, I can't just send E1 to here and send 2E1 somewhere down here. The entire line goes along for the ride. So without knowing that this is a linearly independent set, now we know from a different construction that it is, but we don't know that construction is the same as this one. We cannot just define this map going backwards and say, hey, look, there it is. That's a little bit of a circular argument. Because we could always do that. We could always just, given any map, say, let's define it backwards, and there's our inverse map. So what can we do? Well, we can define a map beta tilde from the free vector space that we just encountered, F sub U cross V to W, by sending the basis element. Well, before I get there, let me remind you that basis elements have the form E sub U comma V, and so U generally is going to be a finite sum of AI UI, and V is going to be a finite sum of BJ Vj. So we want to send E sub sum of AI UI, comma, sum of BI Ji to the sum of AI Bj times Wij. Okay, so why are we doing this? I will leave it as a homework exercise to verify that the null space of this map, beta tilde, contains the null space of our quotient map we saw in the previous slide. So remember what that is. That is just the map that sends this basis element to the sum of AI UI tensor BJ Vj. It was technically a quotient map, and this is an equivalence class. So this is Q, and this up here is beta tilde. So in other words, anything that gets sent to 0 by Q also gets sent to 0 up here. Okay, so what good is that? Now, I should say something about the universal property of quotient maps. I don't think I put this in a lecture, but it's something that I assigned for my regular class as homework. So it's worth mentioning it here. And it is that if you have a vector space X, and suppose that you have a quotient map, let me call this Q. So let me say that it's X mod Y. And so the null space of Q is the subspace Y. Then if we have any other linear map, what do I want to call this? How about F to some other vector space, let's call it Z, then if the null space of Q is contained in the null space of F, let's think about what that means. That means that we are collapsing more to go to Z than we are collapsing here. So we're collapsing strictly less, or not necessarily strictly, we're collapsing not as much to go down here as we are over here. And of course, what we can do is this is going to be isomorphic to Z mod some other vector space, let's call it N. So then there is a unique map G. So if this relation holds, then there exists a unique linear map G from X mod Y to Z such that this diagram commutes, which means that if we do Q of G, we get F. So one way that people like to say this is that this map F factors through the quotient. So you can really think of it as we start here, we quotient out by Q, and then we further quotient out by what's left in the null space of this map that we have not yet collapsed. And that's going to be the picture that we have right here. Is in this setting, we are going to have this beta tilde up here, and we're going to have this Q here. And because the null space of this map contains the null space of this map, we can construct this map G. And we also have no choice as to where how this map is defined. So if we take any element down here, let's say X bar, and then where do we send X bar to over in here? Well, we just pull it back to X over here, and then we apply this beta or this F map, and wherever it gets sent, that's where we have to send X bar down here. Here is a diagram of that. Since the null space of beta tilde contains the null space of Q, then this map beta tilde factors through the quotient. And remember, this quotient is U tensor V. And so that means that this element down here, which now remember, I think this is slightly different than how I wrote it above. This is equal to the sum of AI UI tensor BJ VJ, which if you prefer is the sum of AI BJ times UI tensor VJ. All of these are the same. And how do we define this map beta? Well, we take the preimage of this. This thing goes up here, and then we apply beta tilde, and it gets sent here. And so that means that, yes, we actually do have a well-defined map that sends this element down here, however you want to write it, up to the sum of AI BJ Wij. And that was the issue that we had up here, is we didn't know that we could define such a map like this. And well, it's not necessarily clear that this is the map, this inverse map up here, but it's not hard to check that. I will leave it as a homework exercise to verify that the maps alpha and beta are indeed inverses, because alpha of beta, so going back up here, if this is alpha and beta is going back here, then alpha of beta means do beta first, then alpha, is the identity map on U tensor V. And beta of alpha means start here, do alpha, then do beta, and that's the identity map on W. Now we come to the so-called universal property of the tensor product. And let me one more time remind you of the universal property of the quotient map, which we just did in the previous slide. So this says that if you have a quotient map from x to x mod y, let's call it Q. So here the null space of Q equals y. This sends x to x bar, just the equivalence class mod y. Then if we have any other linear map, F, to any other vector space Z, and as long as the null space of Q is contained in the null space of F, then there exists a unique linear map G from X mod Y to Z that makes this diagram commute. So such that G of Q equals F. So you can think of this as saying anytime we have any map F that collapses at least Y, then that map factors through the quotient space. So we can first collapse by Y and then collapse by anything else that remains to get Z. So equivalently, this X mod Y is, well, in some sense, the largest quotient space that collapses Y. So it's the largest image that has a certain property, and that property contains Y. So that's what the universal property of the tensor product will be as well. So now so here we have a canonical quotient map Q. Up here we're going to have a canonical map tau that just sends an ordered pair in the Cartesian product U cross V to the pure tensor U tensor V. So you can think of this as some sort of quotient map as well. The following universal property says that every bilinear map from X cross U can be factored through the tensor product U cross V. Formally, we have to show that for every bilinear map beta from U cross V to X, for any vector space X over K, there is a unique linear map L from the tensor product to X such that beta equals L of tau. So do tau first, then do L. In other words, beta factors through, any bilinear map factors through U tensor V. One way to think about it is U tensor V is literally the largest image of a bilinear map. Just like how X mod Y was the largest quotient of X that collapsed Y. Okay, so I will actually leave the verification of this on the homework, but I will outline how it goes. So you basically have to define such an L and show that it works. So show that it's linear. And element-wise, if we have U tensor V here, well, so where do we send this thing to? Well, we pull this back to U comma V and via tau, and then that, for this to be well defined, we have to send this to beta of U comma V. So in other words, L of U tensor V equals beta of U comma V. Now to show this is linear, we have to show that it is, that we can pull apart sums and pull out constants. So in other words, we first have to show that L of U tensor V plus, or say U1 tensor V1 plus U2 tensor V2 equals, now let's think about what to do next. Now we can write this as L of U1 plus U2 tensor V1 plus V2. And now we can pull this back. So this, by definition, where does this get sent up here? Well, we pull this back and we apply beta to u1 plus u2, comma v1 plus v2. And then where you want to end up with is that this is equal to L of u1 tensor v1 plus L of u2 tensor v2. So we started here and we want to end up here, and I'll let you fill in the details. And similarly, we also need to show that you can pull out constants. So L of C of u tensor v. So this is, now we know, I'll do it down here. We know we can write this as L of cu tensor v. And so we can write this as, by definition, L of this element, we pull it back up here, and we get, and this is beta of cu comma v. And eventually what we want to get is C of L of u tensor v. So I'll let you fill in those details as well. But that's really all you need to show. And to show uniqueness, I put uniqueness here because typically these are universal properties are a phrase in terms of uniqueness because they are unique, but really this definition is forced. Uniqueness almost comes for free. If you define what this is on a basis, then it will extend linearly and you're home free. So what good is this universal property? Well, some books and sources actually define the tensor product in this way. They say the tensor product morally should be the largest image of a bilinear map. So they say it is whatever abstract vector space T satisfies this property. And then they go about constructing this thing, as we did, and showing that it works. And that's one way to do this. The universal property can also provide us with alternate proofs, or maybe I should say alternate verifications of some basic results, because there's a lot of ways to define and construct a tensor product. We've got to be really careful with circularity here. So I'm going to say that this is a good way to verify that UI tensor Vj is linearly independent. Although I think we can probably modify it to if we had done the universal property earlier, we probably could have actually proven it this way. But again, we have to be really careful with circularity. So how does something, knowing what we know now, how would we verify this? Well, one way that we could do is take an arbitrary linear combination, Cij of ui tensor Vj, which is equal to 0. And the preimage of this is one preimage is going to be Cij ui comma Vj. Notice another preimage is by putting the Cij over to the right-hand side. So this is a preimage under tau. And now let's apply to this Fij, where this is the basis element of the bilinear forms of u cross v to k. So remember, Fij of, I should be careful, u k comma vl is going to be equal to 1 if I equals k and j equals l and 0 otherwise. So Fij just picks off the coefficients, or the product of the coefficients in the ui vj element and sends the rest of them to 0. So this is going to send this to Cij, and then this L maps, so we know that we have a linear map L, and any linear map is going to send 0 to 0, so that shows you that the Cij j's here equals 0. So that's one thing we can do. We can also prove that u tensor v is isomorphic to v tensor u. Obviously, we do not need the universal property to do that, but it does provide us with a very slick proof. Let me show you how. So if we put u cross v here, and we have tau, the map sends it to u tensor v, then remember, we can put anything we want here for x. So let's put v tensor u. And let me call this map beta. It's easy to check, and I should say that this is defined in the obvious way. U comma v gets mapped to v tensor u. It's easy to check that this is bilinear, and so therefore we have a unique map, linear map from u tensor v to v tensor u. It's easy to show that little u tensor little v gets sent to little v tensor little u. It's clearly a bijection and it's linear, so these are isomorphic. Now again, we could have just defined an isomorphism from u tensor v to v tensor u just directly, but two other things that I will leave on the homework are to show basic properties like the associativity and the distributive law holds for tensors as well. So u tensor v tensor w is u tensor v tensor w. And also u cross v tensor w is u tensor w cross v tensor w. In the beginning of this lecture, I encouraged you to think about the tensor product of vector spaces as the span of polynomials in two variables. So like x to the I, y to the j, where u is the space of polynomials in x and v is the space of polynomials in y. Now, this only tells part of the picture. So it's just a lens into tensor products, but it is still my favorite lens. But it does hide certain things, and in particular, it hides a natural isomorphism from u tensor v to the linear maps from u prime to v. So what the heck is this about? So if u has dimension n and v has dimension m, then a linear map is, well, u prime has dimension n as well. The dual has the same dimension. So this is a linear map from k to the n to k to the m. So this is, in terms of a matrix, this will have m rows and n columns. Now, a linear map like this you can think of as, well, u prime you can think of as a row vector, because I like to think of elements in the dual as row vectors. So this is a 1 by n row vector. Then now we have an m by n matrix, which represents this mysterious linear map. And then the output of this, of course, is going to be an element in v, which, well, if we do multiply it like this, then what we are going to get is a row vector, even though we think of vectors in v as column vectors. But it's, so this is a 1 by m row vector. But remember that these vectors you can think of as tuples. This is just how we orient them to multiply matrices. So I'm going to write this as, so I'm going to think of this as the transpose here, and maybe I'll write something like this. So the transpose of this product equals the transpose of that product. But there's nothing wrong with thinking about vectors in V if you want to as row vectors. Okay, so what this is saying is that this mysterious linear map is somehow this pure tensor, u tensor v, represents a linear map, a matrix. So which matrix is it? Well, I claim it's the matrix that sends L, the linear map that sends L, which is right here, to the vector L comma u, which remember, that is L of u times v. So somehow u and v are involved in this, and it should not be clear from this abstract definition what the heck is going on. So somehow here this thing sends L to L of u times v. So let's try to understand this better. Let's start with a very simple example where we have ui and we have vj. So ui is going to be the vector, of zeros everywhere except in the ith coordinate, and vj is going to be the same thing. So So this is in the ith coordinate, and this is in the jth coordinate. Let me highlight this in red just so you can see it. So ui is going to have a corresponding element in the dual, which is going to be li, which you can think of as a row vector with a 1 in the ith coordinate and zeros elsewhere. So I claim that in this case, the corresponding map from, or ui tensor vj, you can think of as this row vector. So this is, I'm going to call this li transpose, just to, actually, you know what? I'm going to call this ui transpose, because that's really, sure, it represents li as well, but let me call it ui transpose, times, well, gotta be careful here. What happens if I try to put vj right here, and I take this product, and this is just a dot product, this is a scalar. So I don't want to do that. But what I want to do instead is I want to put this vj right here. So this is 0, 1, etc. And now if I multiply this matrix, so this is a m by 1, this is a 1 by n, now what I actually get is a matrix. I now get an n by m matrix, and I get this matrix right here. So this matrix is eij. It is literally zeros everywhere except a 1 in the ij entry, and it is the product of vj transpose, that's this column vector, times ui. So notice that we have to do this in the opposite order. So this linear map is so in other words, we can think about ui tensor vj as this matrix capital Eij. And that's a linear map that takes any input row vector. Let's call this L, it's a linear combination, Ci, Li. It takes this linear combination, and if you multiply it by it, what you get is a row vector. So this here is in the ith coordinate, and if you multiply that by Eij, you get a 1 by m vector. So this is a 1 by n vector, and then you get a 1 by m vector, and this Ci is now in the jth coordinate. So think about what this is right here. So this is literally Ci times the jth unit basis vector Vj. And so what is this Ci? Well, this is, if you take L and you pick off the ith coordinate, that's actually the evaluation map. So that is L, comma, Ui. Technically, the evaluation map is an element in the double dual, because this is a map of linear functions, or of dual functions. But we can always associate that with vectors. So picking off this ith element is just L, comma, Ui. And so think about how this works up here. So this is, in this case, Ui tensor Vj gets mapped to, so we're taking this row vector L, and that gets sent to L, comma, Ui. So that's Ci times, in the jth coordinate, that's Vj. So to summarize, if we take the pure tensor of two basis vectors, Ui and Vj, then that corresponds to the linear map, which in matrix form is Vj times Ui transpose. And this is how we extend this from pure tensors of basis elements to general pure tensors. So for example, if we have an element in U and an element in V, and we consider the tensor of those two vectors, that is just VU transpose. And that is the following rank 1 matrix shown right here. And notice how every single row here is a scalar multiple. So here we have, so this row is V1, the entry, U transpose. The next row is V2, U transpose, and so forth. So this is clearly a rank 1 matrix. And if you look at the columns, it's going to be the same thing, but with the V. So this is U1, the scalar, times V. This is U2, the scalar, times V, and so forth. So now notice one of the properties that we talked about with tensors is that if we have 3xi times yj, then that should be xi times 3yj. And notice how that makes sense down here. So if we have, so 3 ui tensor v is just going to be 3 v, or, well, it's I guess technically it's v times 3u transpose, and the 3 just comes out in front because that 3 comes right there, and all that does is that just sticks a 3 in front of every single entry here. And that'd be the same thing if we had, instead of putting the 3 here, so notice how 3u tensor v is v times 3u transpose, and that's obviously equal to u tensor 3v because that is 3v times u transpose. So the basic property about constants going back and forth across the left and right hand side, as we saw with polynomials, is basically just the associative property that we get when we multiply two polynomials or two vectors together. I want to finish with one more way to think about tensors, and it's a way to extend a vector space over R to a vector space over C. So let's let X be a real vector space with basis x1 up to xn. And notice that the complex numbers form a two-dimensional real vector space with basis 1 and I. Now, we have not done eigenvalues and eigenvectors in this class. That's going to come up next. But since an introductory linear algebra course is a prerequisite of this, I'm assuming that you've all seen them. So I'm going to use this as an example. And this whole slide, this whole example is not necessary, but I think it's a neat way to think about tensors. So if you haven't seen eigenvalues and eigenvectors, feel free to just skip this. But I'm assuming that most of you have seen it. So let's suppose that we have a matrix A. It could be n by n. And it has eigenvalues plus and minus I. It might have other eigenvalues, but let's say that plus or minus I are two eigenvalues. Suppose now that V is an eigenvector for the eigenvalue I. Remember what that means is that means A times V equals I times V. Then V is going to have to contain some non-real number in it. So technically, V is not actually in our vector space X, because X is a real vector space. All vectors in X can be thought of as n tuples of real numbers, not complex numbers. So this eigenvector, we know it exists. It should live in some extension of X. It basically should live in the vector space, which is the same thing as X, but our coefficients are no longer real numbers, they are complex numbers. In other words, in this bigger vector space, we want to have vectors like ZV, where Z is a complex number and V is a regular old vector. This is how we extend vectors from having real coefficients to complex coefficients. What we really want is C tensor X, because the basis of this is just 1 tensor x1 up to 1 tensor xn, and I tensor x1 up to I tensor xn. Remember, it's just products of these guys with these guys. Now we can really think of this as, well, the first n as just being x1 up to xn times 1, and the last n as being I x1 up to I xn. So this is how we can formally construct an extension of a vector space by making the field larger. Notice how the associativity that we would expect in this vector space comes for free with the tensor product. And let's compare it to the other examples from this lecture where we have seen how that property of numbers going back and forth across the tensor symbol from the left to the right is basically just associativity. In other words, in this setting, 3i times v should equal I times 3v. So this is like 3i tensor v equals I tensor 3v. In our first setting of vector spaces of polynomials, 3x to the I tensor y to the j has to be equal to x to the I tensor 3 y to the j. In the previous setting with linear maps, 3u tensor v has to be equal to u tensor 3v, and that's exactly what happens in general with the construction of the tensor product. Okay, that is a good place to stop. And next we will talk about eigenvalues and eigenvectors. So if you didn't recognize this example up here or feel rusty about this, make sure to stay with us. See you then.